Okay, hello everyone. Now chapter 13, part 2. Let's talk about colligative properties. So colligative properties depend only on the quantity, not on the identity of the solute particles. That means it does not matter if it's sugar or sodium chloride, it will matter about how much you are adding. And among the colligative properties, we have vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure, right? So for the vapor pressure, like here, you have the first one here, right? Only solvent here, volatile solvent particles in equilibrium. Then if you add non-volatile particles, like non-volatile solute particles right here, will be more difficult for the molecules to evaporate. So this is why if you add solute here, like here you have the solvent, only the pure solvent here, right? But if you add solute, it will be more difficult to evaporate. This is why if you add a solute in the solvent, the vapor pressure will decrease. So have vapor pressure lowering if you add non-volatile solutes. And then equilibrium is reestablished with fewer molecules in gas phase. Okay, now let's talk about Raoult's law. The vapor pressure of a volatile solvent over the solution is the product of the mole fraction of the solvent times the vapor pressure of the pure solvent, right? It's like here. The pressure, to find the pressure of the solution, we're going to multiply the mole fraction of the solvent, multiply the pressure of the pure solvent. So we're expecting that the pressure of the solution will be lower than the pressure of the pure solvent. So in ideal solutions, it's assumed that each substance will follow Raoult's law while in the mixture. Right? So, and then how can you find the mole fraction of the solvent here, right? It is the mole fraction of the solvent is equal to the moles of the solvent, right? The solvent divided by the moles of the total. So the moles of the solvent plus solute here. So in the bottle, going to be the moles of the solute plus solvent. So expecting here, your mole fraction should be below 1. That's why here, if you have this X below 1, when you multiply this number below 1 times the pressure of the solvent, your pressure of the solution will be lower than the pressure of the solvent. Right. Okay, so we have here this praxis problem, right? To find the volatile non-electrolyte with a density of 1.25 grams per milliliter at 25 degrees Celsius, calculate the vapor pressure at 25 degrees Celsius of a solution made by added 50 milliliters of glycerin to 500 milliliters of water, right? And then the vapor pressure of the pure water is this one. So you need to find here the mole, the mole fraction of the solvent here. right? Okay, so this one here, you need to calculate the mole fraction, right? Mole fraction is equal moles of the solute of the solvent here, right? Divided by the moles of the solution. Okay, so the moles of the solvent here is moles. To calculate the moles, you need to get mass divided by molar mass, right? Mass divided by molar mass. Okay, so what's the mass of the solvent here? The solvent is the water. We have 500 milliliters of water right here. But the density of the solution, it is 1 grams per milliliter. So if you convert it from milliliter to grams, you have 500 grams, right? Divided by the molar mass of water. So I have 500 grams of water divided by the molar mass of the water, that is 18 grams per mole, right? And then there's going to be equal to 27.7, like 80 moles, right? Okay, now let's do the same for the solute. Then let me go here in the top. I'm gonna use this area here. So the moles of the solute is equal, I assume here that we have a 20, you have 50 milliliters of glycerin, right? In the glycerin density, it is 1.26 grams per milliliter. Okay, right? Like, let's convert this, right? From density, let's convert it milliliters to grams. 1.26, the density. So to convert it from 50 milliliters to grams, we're going to multiply 50 times 1.26, and you have 63 grams of glycerin. And the molar mass of glycerin here will be 36 plus 8 plus 16 times 3, so you're going to be 92, right, grams per mole. Yeah, in 63 here, that should be 63 grams here. Okay, so how much you'll have here? 63 divided by 92, it is 0.68 for 8 here, moles. Okay, so to calculate the mole fraction here, let me clean here, right? So you had the mole fraction, right? You're going to be the moles of the solvent that was 27.78 divided by the moles of the solute that is 0.6848 plus the moles of the solvent, right? So you're going to divide the moles per mole, so you're going to have a new unit here. It's 7.78 divided by 0.68. 0.68 for 8 plus 27.78 So the mole fraction here is 0.97. Let's do 6 here. 6. No units. So what we're going to do here, we're going to multiply this mole fraction by the pressure of water, right? So the pressure of the solution, right? The vapor pressure of the solution is equal, the mole fraction, 0.976 times the pressure of water, that is in here, 33.8 torr. So times 23.8, you have, will be 23.20. Okay, 22 torr. So the pressure of the pure solvent was 23.8. But when you add the glycerin to the solvent, when you add glycerin to the water, the pressure of the solution now will change to 23.2 torr. Okay? Let me clean here. Okay. So now about the boiling point elevation. Since the vapor pressure are lowered for solutions, it requires a higher temperature to reach the atmospheric pressure. So if you add a solute in the solvent, the boiling point will be higher. Now, and to calculate this, what going to be the new boiling point, we're going to have this equation. And the second one is to calculate the new freezing point. So let's go here. For the boiling point, delta TB, the pressure, right? Boiling point, the pressure, boiling point elevation. The boiling point will be higher if we add a non-volatile solute to the solvent. So it will be delta TB is the boiling point of the solution minus the boiling point of the solvent is equal to I as the Van Hoff factor times Kb, the boiling point constant. Each solvent will have a different boiling point, boiling point constant, times molality. Molality is mole of the solute divided by kilograms of solvent, right? And now delta TF, F for freezing point. So have a freezing point of the solution is minus freezing point of the solvent is equal to minus I, freezing point constant, times molality. Okay, so you have here, right? So the molar boiling point elevation and the freezing point depression constant. For each solvent, you have a different value of Kb and Kf, right? Okay, so then this problem 2 here, a solution of your non-volatile, non-electrolyte was prepared by dissolving 0.250 grams of the substance in 40 grams of carbon tetrachloride. So the boiling point of the result solution was 0.357 degrees higher than the pure solvent. So you know that your delta TB here will be 0.357, right? Okay. 0.357 is equal to I. So here you have is a non-volatile, non-electrolyte. So when you have this non-volatile electrolyte, your I will be equal to 1. Okay, Kb. What's the Kb for carbon tetrachloride? It will be 5.02, right? So that multiply here, 5.02. And then times molality. So you need to rearrange here to find the molality, right? Would be equal to what? 0.37, 0.357 divided by 5.02. So your molality here will be 0.07111. Molality is mole per kilogram. But the question is asking for the molar mass of the solute. So here, let's see here. Okay. So what's the molality formula? Molality is equal moles of the solute, right, divided by kilograms of solvent, right? Okay, so let's do here. Molality is 0.0711 mole per kilogram, equal to moles of the solute that we don't know yet. Moles of the solute is the unknown here. And then divide by kilograms of solvent, that is, the solvent here is this 40.0 grams of carbon tetrachloride, so we need to convert it to kilograms, be 0.04 gram, oh, sorry, 40 grams. Oh, okay. And then find the moles of the solute here. We'll end up with the multiplying 0.0711 and multiplying by 0.0400. So the moles of the solute will be 2.84 times 10 to the minus 3 moles. Right now, okay. Then the next step here, you have the moles of the solute. The question is asked for the molar mass of the solute. So the solute, we don't know the solute, right, is unknown. That is 0.250 grams. So you have the moles, you have the grams, so you can't find the molar mass. So moles is equal to what? Mass divided by molar mass, right? So if you rearrange it here, your molar mass is equal to mass divided by moles. That means here, your mass is 0.250 grams divided by the moles, 2.84 times 10 to the minus 3 moles. Your answer here will be what? 2. Oh, sorry, it's 4, right? Okay, and then you are going to find here the molar mass, do this division here, the unit will be grams per moles, right? Okay. Gram, it's just a G. Okay, now let's talk about osmosis. Osmosis, some substance form semi-permeable membranes. Allow some smaller particles to pass through, but blocking larger particles. In the net movement of solvent molecules from solution of low to high concentration of solute across semi-permeable membrane is osmosis. So the applied pressure to stop it is osmotic pressure. So here you have, right, this tube here, U-tube, and you have one side only the water. In the side here from the right, you have mixture, right? You have the solid, so you have a solute and solvent, right? So, and then at equilibrium here, you see, are you seeing the particles from the water passing to the second tube here, to the right side of the tube, right? Here, are passing here. But if you apply the pressure, the water molecules will return to the original location here. And then osmotic pressure is a colligative property, right? That is pressure, osmotic pressure is the symbol here, this pi, is equal to I as the Van Hoff constant, multiplied by moles divided by volume, multiplied by universal gas constant, multiplied by T. So what's moles divided by volume? It's a molarity, right? So you can write this formula like this, going to be equal to I times molarity times universal gas constant times temperature in Kelvin. So if you choose solutions separated by semipermeable membrane, they have the same osmotic pressure and no osmosis will occur. So types of solutions in osmosis. Isotonic solutions, iso means the same, right? That means isotonic solution, same osmotic pressure. Solvent passes the membrane at the same rate both ways. If you have a hypotonic solution, the low osmotic pressure, right? The solvent will leave the solution at a higher rate than it enters with. And if you have a hyper, right? Hyper means higher, and the hypo means lower. Hyper for hypertonic solution, the higher osmotic pressure will enter the solution at a higher rate than it leaves with. Okay. So let's see this. Osmotic and blood cells. Red blood cells have semipermeable membranes. If stored in a hypertonic solution, they will shrivel as water leaves the cell. That's called crenation. So you have here this first one, red blood cells in the isotonics medium, that means the same concentration inside and outside, right? And this one here, you have a crenation, right? That red blood cells placed in hypertonic environment. So the ones inside here will live lower solute concentration. Inside and outside, if you have it higher, the system will live here. And then the opposite here, for homolysis of red blood cells placed in hypotonic environments. So have a low solute outside concentration, and inside you have a high solute concentration. Then the next topic here is colloids. Suspensions of particles larger than individual ions or molecules, but too small to be settled out by gravity, are called colloids. Colloids form the dividing line between solutions and suspensions. Types of colloid. So you have the phase of colloid, right? Gas, liquid, solid. And if you have the dispersion-like substance, if the solvent is gas, and if the solute is gas, we will not have a colloid here. There is no example. If you have both gas, they will have a solution, will not be a colloid, you have a solution. So, and if you have a gas as a solvent, the solute, and the solid as the solute, you have a colloid type is aerosol. Aerosol. In example, have a smoke here. If you have the dispersion, the solvent like is a liquid, and the dispersed solute is a gas, you have a colloid type is a phone. So example here, white rim. And then if you have the solvent and the solute are liquids, you have the emulsion, example, have the milk. And if you have a solid as the solvent and liquid, and the gas has the solute, you have a solid form that we have example marshmallow. And if you have a dispersion solvent like solid and the solute is liquid, you have example butter. And the classification of colloid is solid emulsion. Colloids and biomolecules. Some molecules have a polar, right? Polar, the water is polar, right? Example. That means if you have polar molecules, so polar molecules with water will have attraction, right? Because it like dissolves like. So here, hydrophilic means water loving. So some molecules have a polar hydrophilic, water loving end, and a non-polar hydrophobic water fearing end. In larger molecules that forms colloids in water often have the hydrophilic portions face outward to interact with the water, because water is polar and the hydrophilic means water loving. And then we have here colloids in biological system. Colloid can aid in the emulsification of fats and oils in aqueous solutions. An emulsifier causes something that normally does not dissolve in a solvent to do so. So that's the end of chapter 13, right?